최근 테크놀로지 같은 경우에는 어떤 코에피션트를 잴 때 이제 아이소서멀 상태에서의 코에피션트를 잰다고 합니다. 이제 문제가 있었는지 많이 바꿨다고 하더라고요. 그래서 그걸 이제 정의한 게 이제 μt라고 해서 어떤 엔탈피의 변화를 이제 프레셔의 변화에 따라서 보는 거고, 그때 이제 컨디션 이제 아이소서멀 컨디션인 거고요. 그래서 요거 같은 경우에는 그때 이제 엔탈피의 디퍼런셜레이션 여기 텀이 나와 있잖아요. 이거를 저희가 이제 μcp라고 정의를 했었고, 요거에 이제 결국 μt가 된다는 어떤 정의에 관한 거였는데, 그걸 이제 좀 빠뜨려서 오늘 얘기를 잠깐 했고요. 그리고 이제는 이제 챕터 3 수업을 나가도록 하겠습니다. 영어로 수업을 할게요. So in this chapter, we will learn an important concept of entropy, which explains why some physical transformation or a chemical reaction are spontaneous. And then second and third rule related to this entropy, and also another important thermodynamic property, which is Gibbs energy. So last time we learned about the first law, but it has a major limitation. The first law states that the total energy of the universe does not change in any processes, so it cannot predict the direction of the spontaneous change. So we need the different thermodynamic property, and it turns out that the direction can be determined by the manner in which energy or matter are distributed. So this concept is made quantitative by introducing the property known as entropy. So this change of entropy provides the necessary criterion for predicting the direction of any process. So let's see what is the spontaneous process. It is one that occurs naturally under the given set of conditions without requiring the external energy input. So it's also defined by the fact that the reverse process does not occur under the same conditions. So there is a example of a spontaneous process, like there is a ball bouncing on the floor, and the ball does not rise as high after each bounce because the sum of energy associated with this motion is spread out into the sum of motion of the particle in the ball or the floor. So this arrow indicates the relative amplitude of a summer motion of molecules, and as you can see, it is getting larger after a bounce. So the direction of a spontaneous change is toward the state where the ball is at rest with or its energy dispersed into this disorderly summer motion in surrounding. So the kinetic energy of the ball is transferred as a heat to this floor, and then you can see that the summer energy of this floor becomes larger. And so this is a spontaneous reaction, spontaneous change. But in the case of B, a ball is resting on the floor, but it cannot spontaneously rise into the air by absorbing summer energy from the floor. This is a highly improbable event. As you can see in this cartoon, at the first place, the ball rests on the warm surface, and some of the summer motion is accumulated. And all of a sudden, random disorderly motion is localized and directed orderly motion to the same direction of the ball to move upward the ball. but as you can imagine, this is impossible. So the thermal motion cannot be suddenly ordered like this or localized in the same direction, and they cannot move the ball to upward. So the heat is on a random summer disorderly motion. So we can say that the spontaneous change are always accompanied by a dispersion of energy and matter. For example, let's think about the gas expansion or fluid momentum and heat transport, which is that this energy is applied into a more disorderly form. So for bouncing on the floor is also one of the examples we already see in the previous slide. So what we run here is that the direction of spontaneous change is to dispersion of the total energy of an isolated system into surroundings. So this principle accounts for the direction of change on the bouncing ball because its energy is spread out as a summer motion of atoms of the floor, and the reverse, bouncing from the floor, is not spontaneous because it is highly improbable that energy will become localized, leading to uniform motion of coarse atoms. It is impossible. But you might think that the direction of a spontaneous change follows a decrease in energy, but let's think about the ice melt at the room temperature. So it is a spontaneous reaction, but the internal energy of a system increases because as you know, the liquid water has a higher internal energy. So it means that the internal energy of the system increases, but it is spontaneous change because of this entropy increases. So we need the thermodynamic function to predict this kind of direction of spontaneous change, which is entropy S. And we will gonna run through this chapter. Let's talk about the second law. The second law of thermodynamics expresses these conditions more precisely in terms of classical concept of heat and work. One statement was formulated by Kelvin. He said that no process is possible where the sole result is absorption of the heat from a reservoir and its complete conversion into the work. This meaning is that the conversion efficiency can't be the 100%. So let's see his statement a little bit more. If you see this figure, Kelvin's statement denies the possibility of the process of this figure. So in the figure B, heat from the hot source is completely converted into the work by this engine without any loss, meaning it's 100% conversion efficiency. As you can see that this process does not violate the first law since the total energy is conserved. Like at first it is conserved as a heat, and then now it is conserved as a work, and this efficiency is just 100%. But as you imagine, this is impossible according to the second law. Then to convert the heat to work, the idealized device of heat engine should be the left figure A. So this heat engine consists of two reservoirs. One is hot and the other one is a cold sink, and they are connected through this converter. That this converter can convert some of the energy flown as heat into the work. So conversion efficiency is not 100%. So some of energy loses as a heat, and only the sum of energy can be converted to the work. There is another statement from Clausius. So he said that heat does not flow spontaneously from a cool body to a hot body. This heat flows from the low temperature to high temperature is not spontaneous. And if this happens, we need the work to achieve to make a heat flow from a cold source to the hot sink. Okay, so there are two statements from two scientists related to the second law. Now the second law can be expressed in terms of entropy as the entropy of an isolated system increases in the course of spontaneous changes. So this means that the total change of S is positive. This total entropy is include the entropy of the system and entropy of the surrounding. So be careful. This includes all of system and surrounding, like the universe. So let me explain a little bit more. So if there is a system, let's say that the outside is surrounding. So we call the universe include the system and the surrounding, and then this is the isolated system. The outside is just isolated universe, and there are two boundaries. Like boundary number one is between the system and surrounding. This boundary is defined by the relation between the system or surrounding. Like we can say, if we can say this is a diabatic boundary, that means that Q is equal to 0. It does not flow. And there is a second boundary, between the surrounding and outside the universe, which is because this universe is the isolated system. Isolated universe, so this boundary 2 does not allow for the exchange of energy and matter. So when we say that total entropy, we are considering both the entropy of the system and the entropy of the surrounding. And for a spontaneous change, the total entropy increases. So this is the second law, which is expressed by the entropy. And we can define the entropy with two approaches. One is the classical, and the other one is molecular. Here we will gonna define the entropy. We are gonna define the entropy by the thermodynamic definition. So the thermodynamic definition focuses on the change in entropy ds that occurs in a physical and a chemical change. And this definition is motivated by the idea that a change of energy is dispersed in a disorderly way, depends on how much energy is transferred as a heat, not as a work. So let me remind this figure. So as you can see, this is a heat. This is a work. So this heat simulates the random motion of atoms, while this work simulates the uniform motion of atom. so it does not change the extent of disorder because like you can see that if you apply the work, the atom moves the direction along the work applied, so there is no disorderly motion here, so entropy does not change. Only heat can change the entropy. In this system, entropy changes. And finally, the thermodynamic definition is ES is equal to the dq reversible over T. And this Q is heat supplied reversibly at absolute temperature T here. And for the measurable change between two states, like initial and final, that means that del S is integral of dq over T from the initial state to the final state. And as you can see that the unit is Joule per Kelvin. And I also want to add that the entropy is an extensive property and it is a state function, but about the state function we will gonna discuss later in this chapter. And let's see how the definition is used to formulate the expression for the change in entropy of the surrounding ES. So let's start from here. Let's imagine like there is a infinitesimal chain transfer of a heat Q from a system to the surrounding, and as you imagine that this surrounding is much larger than the system, whatever, so the volume and the temperature surrounding volume and temperature is a constant, whatever the system, whatever happens in the system. And and the energy supplied from system to surrounding can be expressed as the internal energy change of the surrounding. And then by the first law, we can say like this, and the work is expressed like this, but the surrounding, the volume is not changed, so we can remove the work here. So meaning that the internal energy of the surrounding depends on the dq supplied from the system. And as you know, like the internal energy is a state function, so it doesn't matter whether the Q is reversible or irreversible. So we can say that like by the definition of entropy, here the heat term is reversible, but in this case, under this condition, this dq is the internal energy change, and then this internal energy change doesn't matter whether it is reversible or irreversible, so we can just write like this. Let's say that this is just the dq. And then finally, by the definition, we can say that the surrounding of entropy change is dq or dq surrounding and temperature of surrounding here. And then for a measurable change, you can write we integrate these two both sides. Then dq becomes a q, and as we say that this surrounding is so large, so the temperature does not change, it comes like this. So this means that regardless how the change brought about in the system, reversibly or irreversibly, the change of entropy of the surrounding is calculated by this one, like dividing the heat transferred by the transfer to the surrounding over the temperature at where the transfer takes place. And for example, on case like for the adiabatic process, the surrounding is equal 0 because heat cannot transfer in this system. So this means that the entropy change of a surrounding comes to 0. Let's see the next slide. And we are gonna discuss how the definition of entropy is consistent with the Kelvin statement and then Clausius statement. So what Kelvin statement says that the no process is possible where the sole result is the absorption of heat from a reservoir and its complete conversion into the work. So like this, the 100% conversion of heat to work is impossible. So let's see this device here, like which violate the Kelvin statement. So let's think about the entropy of a hot source is reduced as the energy leaves it as a heat here, and we can see that because of definition of Q is negative because this energy leaves from the hot source, the system. This means that the entropy is negative here. And as we learned, like work does not produce any entropy. So overall, the system, the entropy of the system decreases. This means that the second law say that such a process is not spontaneous. So this device cannot produce any work. So this means that the definition is consistent with the Kelvin statement. And let's see the Clausius statement. What Clausius statement say that the heat does not flow spontaneously from a cool body to a hotter body. Let's see that. Like the entropy of the cold source decrease when the energy leaves it as heat. So I just write here. But when the heat enters the hot sink, entropy rises because Q is positive. But as you can see this equation, when the temperature is higher, entropy is lower. So like the increase does not match to this decrease. Like the decrease is much larger than this increase of entropy. That meaning that overall there is a decrease in entropy. So the transfer of heat from a cold source to a hot sink is not spontaneous. So we just see that our thermodynamic definition is consistent with these two statements. And let's see the statistical view of entropy or the molecular interpretation of the second law. So this idea comes from that atoms and molecules are distributed over this energy state available to them according to the Boltzmann distribution. So this follows that when the temperature is increased, the molecule populated higher energy state, like in this figure, at the low temperature, molecule usually populated here. But if the temperature increases, as you imagine that they can occupy the higher energy, meaning higher state of energy. And Boltzmann proposed that there is a link between this spread of molecules over the available energy state and the entropy, which can express as like this equation, as is equal to the K ln W. K is the Boltzmann constant, and W is the number of the microstate. The microstate is the number of ways where the molecules of the system can be distributed over the energy state for a specified total energy. Like how this molecule occupied in this its microstate, which this is an expression of W. So this concept of the number of microstate makes the quantitative and qualitative concepts of disorder and the dispersion of the matter and energy. So for example, if all molecules are in one energy state here, all molecules occupied only one microstate, which means that W is 1. So meaning that it follows the entropy is 0. So there is only one way to achieve a given energy, and then there is no disorder, so entropy can be 0. But if W is larger than 1, it means that the molecules spread out over this available state. Therefore, S is greater than 1. So like you can think of like a molecule can occupy here and here and here, meaning that the disorder increases. So meaning that it leads to the entropy increases as well. So W increases if the separation of energy state decreases because more states become accessible. Let's explain this. Like if you see this example of a gas expansion confined to a certain container. So when the container expands from top to bottom, as you can see, the translation of energy states move closer together. This is very close compared to this microstate. That means that the more microstate states become accessible to the molecule. As a result, S is increases. This means that when the gas expands, these gases molecules disorder increases, leading to the entropy increases as well. Let's see another condition. So this molecular interpretation of entropy helps us to explain why the entropy changes depends inversely on the temperature in the thermodynamic condition. So let's see that this system has a high temperature, so the molecules are spread out over the large number of energy states. But increasing the energy of the system by heat makes the more state accessible, but given that very many states are already occupied, meaning that the W change only slightly. But in contrast, in the case of a system at the low temperature, only a fewer states are occupied at the beginning. But when the energy is supplied as a heat, you can see the more states are accessible, and the change is more significant than at a high temperature. So in this case, the W change is larger, meaning that the entropy change is also larger than the high temperature. 이 부분 나가기 전에 엔트로피에 대해서 잠깐 한국말로 정리하고 그 다음에 이제 스테이트, 왜 엔트로피가 스테이트 펑션으로서 스테이트 펑션인지 이제 정의를 하겠습니다. 이제 그 전에 출석을 할게요.